Good morning, everybody. Nick reminded me that I forgot to do a demonstration for you. Okay, so I'm going to show with a K. Keep doing that. Nico. Sorry, Nico. Why you should never put anything that's metal in a microwave, which is false. You should never put anything that's pokey and metal in a microwave. What is this? DVD. Okay? And DVDs are two layers of plastic, sort of, with a metal oxide layer where the data is stored. Okay? And in that metal oxide layer, there's a whole bunch of little pits. Okay? And on those pits that store the data, there are sharp edges. If you do this at home and burn your house down, it is not my fault. Okay? I don't know. Where's the fire extinguisher? Yeah, Sammy's going to be real there. You guys see it? You do it for longer?
10 straight minutes.
Now we know how to describe
You're going to smell it in a second.
Whoa.
Okay. All right. So you can see the paths where the arcs went through the DVD. Turn that around. It's going to smell like burnt plastic. So let's see here. More burnt plastic smell. I'm not going to do all of them at the same time. Seriously. So boring, as you be. All right. I want to rotate it just slightly so people can see it. And then I'll go that way. Right? So. Like down so you guys can see it. So it'll start about a second after I turn it on. Not 55. We ready? Okay, you saw that? All right, let's reset. You ready? Here goes. Ah! I know I did. We'll send this one around. Okay. You can see the path that the arcing took. Right? So, what happened there? A microwave oven. How does a microwave oven work? It uses electromagnetic waves that are called microwaves in order to make water molecules really happy. And the water molecules will jump up and down and vibrate because the water molecules have a resonant frequency the same as the microwave frequency. And it bombards whatever's in there with these electromagnetic waves. Electric and magnetic fields. We'll concentrate on the electric field part. Okay? So we get a big electric field inside of the microwave, and it will gather wherever there are pokies. Remember the pokey on the conductor? There's lots of places for electric field to kind of connect, but inside of a Faraday cage it can't, right? So why is it that the microwave oven is safe for us to stand outside of if there's just this huge electric field in there? Because it's a Faraday cage. Okay? In fact, the door on the front is also Faraday cage. It's a mesh of wire in there, right? Mesh of metal to keep those microwaves from coming out. Okay? The CDs and DVDs arc, okay, because it's just all those pokies, right? The electric field can get really big. Anybody that's ever put a Hot Pocket into a microwave knows how to cook a Hot Pocket in a microwave. What do?
They stopped using the foil.
They still have that little pocket thing, right? That little cardboard thing that you slide over the Hot Pocket. Yeah, they still do. Just buy better Hot Pockets. No, they stopped.
They do it.
Yeah, there's little cardboard sheets. Why? What's the point? What's the Hot Pocket supposed to be? Hot and a pocket, right? And preferably crispy. Anybody that's ever cooked anything in the microwave knows that food gets boiled from the inside out, right? You are turning water molecules into steam and it just kind of tastes, right? Chicken in the microwave is gross kind of thing, right? So how is it that they can get a crispy Hot Pocket in a microwave with that cardboard cover? Because the cardboard has metallic fibers in it. And it heats up like an oven. Not from the microwaves, but from radiant heat, which causes crisping. So why is it safe to put one of those in your microwave? Hot Pockets are safe to put in the microwave. I want to communicate this. Hot Pockets are not safe for you to eat. That's different. That's called nutrition or the lack thereof, right? Okay? But they're safe to put in the microwave. So is a spoon.
It's literally all over there.
Anybody that's ever left a spoon in the microwave probably hasn't noticed. Because it won't spark unless it's got a very sharp opposite end, right? But a spoon is nice and curved and generally won't cause sparks. Anybody that's ever made frozen orange juice from concentrate? Is this a thing anymore? You buy the orange or lemonade or whatever, right? It comes frozen. It's got those two metal caps on the end. Everybody knows you open up one of those ends and you got to get it out, and it's like a solid lump of plutonium inside there. Right? It's like there's meteorites in the solar system that are less dense than the stuff in this can, right? I take the top off, I throw it in the microwave for 30 seconds. Why does the metal bottom not arc? Because it's curved. There's no pokies on it. It's fine. I'm not responsible for any harm that you do to your house, your family, or your microwave. So, there you go. Don't be a pokey in a lightning storm. Okay?
Someone took the sign off.
Yeah, this is the one I did 2 years ago.
Like before.
So we'll just start looking here.
And the whole building had to be evacuated.
All right. What are your questions for me? Yes?
For like the formulas we went over, like wine, spring, disc, those are like general. Should we like review any specific situations?
I mean, you're gonna.
Or should we just all get, oh, it's the hard end?
So you can choose to reinvent the wheel during the exam, or you can have the electric field for a ring on your sheet. And so if you have a ring, then you're kind of good to go, right? Am I going to, on the exam, say, start at first principles and read direct? No, right? But if I ask you to find the electric field of a ring, and you know how to use that equation, game on, right? So I would have the electric field of a ring, electric field of a disk, electric field of a line of charge, both perpendicular bisector for a finite one and for an infinite one. Like, we developed all those things at high cost, right? So those are perfectly valuable and viable to have as long as you know how to use it, right? That's kind of always the trick, isn't it? Arc of charge. You basically have seen all of the Gauss's law geometries. We got spherical, we got cylindrical, and we got linear. So having examples of those to orient yourself, that's what I did. I mean, it's kind of hard to answer the question. You know you best, right? What sorts of things are going to help you. But yeah, having all of those results, it's really nice. Yeah.
Number 9 on 23 homework.
23, number 9. Jumping straight into the homework. I already had it open. Let's see if it messes up on me. It's long. Whenever it says it's long, it means like infinity, right? Non-conducting, solid, has non-uniform volume. Okay, so non-uniform charge density is code language for you will integrate. That's right, okay? It's probably going to be an integral, okay? They give me rho, they give me the formula for that sort of char. Okay, right? Find the electric field both inside and outside this cylinder. The cylinder is 5.6, but at 2.3 centimeters, I'm going to be inside of it, and at 15 centimeters, I'm going to be outside of it. So we got to do both here. So let's see if I can remember how to use my iPad. My iPad tech is not, my new tech has not been working, all that great for doing test reviews. So we'll see if this might blank out on us at some point. Oops. All right. So cylinder. I'm going to draw my cylinder. So there's my physical cylinder, okay? And then we need to go inside the cylinder, and eventually we need to go outside the cylinder. Is that working? A little bit. Okay. So for inside, we're going to employ Gauss's law. It's a chapter on Gauss's law, so let's see if Gauss's law gets us anywhere. Gauss's law, we try really hard to not do the integral on the left-hand side. As a matter of fact, you haven't seen any examples where we actually do this integral beyond writing down what is essentially E times A, and as long as we pick clever, in other words, we got a cylinder, so we're not going to use sphere, we're not going to use a rectangle, we're going to pick cylinder, we should be good to go. So what is the surface area of my Gaussian surface, my red Gaussian surface that's in there? If it's a cylinder. 2 pi r, circumference times the length of the cylinder. So E times 2 pi r, and this is like inside, like this r right there, r inside, times the length of the, okay. And then we've got this charge enclosed over epsilon naught. But to get the charge enclosed, because this density is changing, and they told me how it changed. It's AR squared. To find the charge inside of that thing, I am going to have to integrate, like we did in chapter 21 when we were doing all those charge integrals. So the charge will be the integral of little charge, will be the integral of rho dv. Is everybody okay with why all that got all written down? Hoping this is a little bit reflexive, right? Because we did this in chapter 21. We're going to bust this thing up into some sort of differential volume that takes advantage of the r direction. But now the dv comes, right? And we've done cylinders before. It's just a question of how are we going to cut it. Are we going to cut it like sort of cake layers along the z-axis of the cylinder? Why am I not going to pick that one? There's no z, right? It all depends on r, doesn't it? So how do I cut a cylinder into volumes in the radial direction? It's the nested toilet paper tubes, which is going to be the surface area, 2 pi rl times dr, right? I want to give this surface area some volume, some differential bump outwards in the direction I want to integrate. So that becomes my dv. And, we've covered all the different dvs you could have. There's like 3 different kinds for cylinders. There's really kind of one kind for spheres. Kind of one for boxes, right? Like, we've covered all the geometries. You have all of that in your arsenal. It's a matter of, you don't have to really reinvent the wheel. You have to be good about lining up like what's changing in the problem and that sort of stuff. Okay, so now my charge integral is going to be the integral of rho, AR squared, times dv, 2 pi RL dr. Let's clean that up a little bit. Stuff comes out. Things that are constants in this integral, what are they? A 2 pi L, that's it, right? R cubed dr. We picked up an r squared from the density function and an r from the differential volume. Okay, and those are supposed to be r's, not v's. So we need limits. So for the red one, what's our Q enclosed going to be? We're going to go from the center to r inside, aren't we? What's the integral of r cubed? I tried to draw the 4 first. That's not going to work. R to the 4th over 4. And when we put 0 in, we get 0. When we put r inside, we get r inside. And then we've got our a 2 pi l, right? So there's our charge enclosed. So I can write that up here. I didn't leave myself any space. 2 pi l r inside to the 4th all over 4. Okay, now we got some cleanup to do, right? Clean up on aisle 5. What cancels? 2 pi, the L, and one of the R insides, right? What am I left with? I'm left with E inside is equal to, wow, just A over 4 R inside cubed. Over epsilon naught. Thank you. I always forget epsilon naught. It's always a long. And then I wonder why I'm off by like a factor of 12. And I'm like, oh. All right. So now we've got the values, right? They gave us all the stuff that we needed. That we gave me A. Microcoulombs. What am I going to do with the microcoulombs? 10 to the minus 6. What am I going to do with centimeters? 10 to the minus 2. And I'm going to put 2.3, right? 2.3 times 10 to the minus 2 in there. That should give me part A. Didn't work for you?
No. Well, for part B, it didn't work.
Part B. So what about part B?
Would the parameters be only the cylinder and not the distance of the Gaussian surface?
No, it's just the Gaussian surface. The only thing that matters is what's inside the Gaussian surface.
We're thinking of the other one. It's the shell.
Yeah.
The hollow.
All right, so for outside, again, we do Gauss's law, but do we need to reinvent the wheel here? Can we take advantage of what we've already kind of sussed out? The answer is yes, obviously, because I'm asking it, but what does the left-hand side turn into? Has anything changed just because we are drawing a Gaussian surface outside this thing? Nothing changes. So this side is still going to be E times 2 pi, and now we're just outside times L, right? Where this distance R outside is right there. Okay, Q enclosed. Oh my gosh, I got this big integral. I have to do this integral all over again? No. All of that right there stays identical whether I'm inside or outside the cylinder. Nothing changed in that setup. It's still a Gaussian surface, still cylindrical. I still need a differential volume. What is the only thing that changes? The limits that I take the charge over. I need to add up all the charge. Since my Gaussian surface is outside of this cylinder, how much of the cylinder am I going to integrate over? The whole cylinder. The Q enclosed is a physical thing. It's your actual charge. It's the actual object. The left-hand side is an imaginary surface. It's a Gaussian surface. It's a mathematical construct that Gauss developed to help us connect flux with what's actually physically happening. So our integral of what's actually physically happening needs to represent the physical reality, and it needs to be the amount of charge that's enclosed by our Gaussian surface. How much charge is enclosed by the blue surface? All of it. And so we're going to integrate from 0 out to the actual physical limit of charge. I don't put R outside into my limit. Does the actual physical charge extend all the way out to the blue Gaussian surface? No. It's just the physical cylinder itself. So I will integrate from 0 to R, which is going to make my Q enclosed this time be A2 pi L capital R to the 4th over 4. And so I come over here, a to pi L r to the fourth over 4, and don't forget the epsilon naught. And then do our cancel. Can I divide the r's now?
No.
No, I can't do that, right? But my E outside is going to be a big R to the fourth all over 4 epsilon naught R outside.
I didn't use
That's how I said it.
That's how you say it's still wrong? Then you're arguing maybe with round off error or something like that. So send me what you got and I can give you credit or tell you what they think the answer is. You're probably really close. Just make sure you're putting in centimeters and
Yeah.
all that kind of stuff. But yeah, I mean, great problem. Cylindrical situation. Yeah.
I have a conceptual question that has to do with electric fields inside of the non-conductive.
Okay, inside of an insulator, sure.
If there's a cavity inside of a insulator, at the center of that cavity, is there any electric field?
Depends on what the insulator is doing.
So if it's a uniform density, the answer is there is no electric field at the center. But if it's not uniform density,
Yeah, if it's non-uniform, it can be all over the place.
gotcha.
The thing about conductors is in static equilibrium is that they will always sort themselves out to have those charges as far away from each other as possible. It would be the most energetically favorable distribution of charge, which means that cavities will always have zero electric field in them. With an insulator, because the charge is more than likely going to be non-uniform, we can't say that. If the insulator were perfectly uniform, no, not I was about to say something false. The charge would have to be only on the outside of the insulator for that to be true, which is basically the insulator would have to be like a conductor in its charge distribution. But yeah, insulators, that's a different ballgame. Yeah.
Number 5, please. For chapter 23.
Go to the shower! Okay. Where did you have trouble? Like all of it, or just not getting the answer they got?
I'm just not getting the answer they got.
So, did you put in a minus sign?
Yes.
Because unfortunately they say, and it got me too, what does it say? Negatively charged ions. So like I did it, put it in, and it kept going wrong. I was like, what? That's not wrong. But yeah, you got to put the negative sign on the answer. Okay, so that's not it. Did you get A but not B or anything? You just can't get A?
I can't get A.
Okay, let's do it. I'm sorry for my drawing inability. There's my shower, right? I'm going to call this front face 1. I'm going to call the top one 2, and I'm going to call this side one 3, just so I can reference them as 1, 2, 3. They're telling me that the electric field points outward in every direction at the face of the shower. The words that they use are: the electric field is directed perpendicular to the surface and uniform in magnitude. So that means the electric field, which is the red color, is pointed perpendicular to the surface everywhere. In order to pull off a Gauss's law setup, Q enclosed over epsilon naught, I need to figure out what the left-hand side is going to be, ideally without integrating. But this is the total electric field and the total surface area. But the surface areas are all, there's 3 different surface areas across 6 different sides of this rectangular shower, right? So the flux through side number 1, is it going to be the same as the flux through 2? No, why not? Different area. Same electric field, different area, right? So on the left-hand side, I'm going to have the flux through side 1, and then I'm going to have the flux through side 2, and then I'm going to have the flux through side 3. They're all different. But what about the flux through the opposite of side 1? The one on the back. It's the same as the flux through the front face, isn't it? Area vectors are all pointing out. Electric field vectors are all pointing out. What about A2's partner? Also going to be the same. What about A3's partner? Also going to be the same, right? So I can clean that up a little bit. 2 times E and then A1 plus A2 plus A3 will get me the total flux. In this problem, only because the electric field is the same value through all of those surfaces. All right. Do I know what my charge enclosed is? No. What am I looking for? Charge enclosed. The question wants the charge density. How are we going to find charge density? Q over V. If we can find the charge in this shower, divide by the volume of the shower, then we're home free, right? So solve this for Q enclosed. That's going to be 2 times the electric field times epsilon naught. A1 plus A2 plus A3. It's going to be my charge enclosed. Declan, are you with me? Like, is this all what you did?
No, I was not doing the charge density.
Okay. All right. So maybe that's just where it got hung up. Does anybody else need to see me keep going on this one? How do you find the number of elementary charges per cubic meter? Divide by the charge on an electron. Lots of physics that goes on in the shower. Fluid dynamics, sound and standing waves, if you're singing.
So what's the formula?
For what?
Part 2, part
Part B, they want the number of charge carriers. So you're going to take your charge density and divide by the charge on the electron of 1.6 times 10 to the minus 19 coulombs. And then, yeah, your answer from row. Your answer from part A. Is that right? But did I not carefully read it?
Yeah.
The number of elementary charges per cubic meter. Yeah. So this is going to be coulombs per cubic meter. You're going to divide by a coulomb, and you'll end coulombs per elementary charge, right? And I'll end up with elementary charge per cubic meter. Yeah.
So when we're doing arc of charge, the general equation you gave us was negative cosine theta I hat,
Mm.
sine theta I
Mhm.
hat. But I'm assuming that's when the arc of charge is negative and it's on top.
It's position relative to the origin.
Yeah, it's because I measured my angles from the positive x-axis.
Right, but if let's say the charge in the middle was
Our vector points the same way regardless.
Are you talking
The
about
charge in the middle will just flip the sign on the charge that you put into the equation.
So you're saying if we leave the equation the same, just
Yep.
insert
Put
the-
a negative charge.
Okay. 'Cause I
When you're
would-
using R vector, you have to obey the sign of the charge in the equation. If you're doing it the book's way, you can drop the sign. It's just a magnitude. I know that's confusing, but
No.
it's the rule. R vector knows what to do with the sign on the charge.
So it just takes negative cosine I hat.
Yeah.
number 12, 23? Part D specifically.
D. Because we know what the answers to A, B, and C are.
0.
Why are the answers A, B, and C 0? They are 0, right? Yeah. Because how much charge is enclosed when we're at the center? None. How much charge is enclosed when we're halfway to A? Still none. And how much charge is enclosed when we're at A? Still none. Ooh, they're having fun out there, whatever they're doing. More fun than us. Is that chemistry? What's going on? All right. What, you want to take a guess as to what symmetry we're going to take advantage of here? Spherical? Why spherical? It's a sphere. Try not to overthink that. Okay, so it's a 1.5 A. So that means we're inside, right? We're like somewhere in here. Okay, so I'm looking at Gauss's law and I'm going, all right. Got to figure that out, and I got to figure out the charge enclosed. This is going to be E times 4 pi, we'll just say R squared. Why is it 4 pi R squared? We're using spherical geometry. That's the surface area of a sphere. The Gaussian surface is a surface, right? We use surface area in that. Okay, charge enclosed. Well, that's all the charge that's like right in here, isn't it? Okay. What do they tell me about the charge density?
It's value.
But give me a number. Okay. This can be real easy or real hard depending on how you want to look at it. Can I go and set up another one of these integrals? Sure. Seems like the long way, but that's all right. We'll get to the same answer. So the rho in this integral, because it's a number, 2.18 nanocoulombs per cubic meter, what can I do with it? I can take it out. And if I want to, I can go try to set up a dv, right? Probably onion layers in this integral, okay, and integrate outwards and do all that kind of stuff. Or I can just look at that and go, what's the volume? What's the volume of a sphere that's covered that has charge enclosed in it? The volume of the sphere is 4/3 pi r cubed, isn't it? So what's the volume of the red shaded area?
But it's from the inner radius to the enclosed radius.
It's going to be, 1.5 a cubed. Here, I'll write it in even more generic terms. It's going to be r furthest r cubed minus 4/3 pi inner distance cubed. This integral right here literally just says, what's rho times the volume of that's enclosed? Okay. Again, if you kind of want to fall back on what we've always done, this is rho times 4 pi r squared dr. 4 pi. And what is the integral of r squared dr? R cubed over 3. And what are the limits? Well, it starts at a and it goes out to 1.5a for part D. Okay? We end up with exactly that right there. And this is kind of the generic volume. The reason this works is because the volume function is a constant. Technically, we integrate to find it still, but we really don't have to integrate because it's just constant. And so if I know how much volume I've got, I'm done. I just multiply by the density, and I've got my total charge. So this is going to be 4/3 pi, and then we'll just go R2 because I'm being lazy, cubed minus R1 cubed. And for part D, this is going to be 1.5a, and this is going to be A. For part E, what are we going to put in? Yeah, for this, so then the R2 is going to be B, which is equal to 2A, and R1 is just going to be A, right? And you kind of just rinse and repeat this. For parts D, E, and F, does the left-hand side change? Kinda. What's the R that we put in on the left-hand side? It's always the radius of the Gaussian surface, right? So we would put in 1.5A here for part D. For part E, we would put in B, or 2A as they tell us in the problem. And then for part F, 3B. Now, for part F, where we're going to put in 3B, which is the same as 6A, what do we put in for the charge enclosed? It's just B to A. Why is it just B to A?
Because that's what it's.
That's the physical thing, right? Even though we're doing a Gaussian surface way outside, okay, this sphere, to calculate the charge enclosed, we use the actual physical charge distribution. So we don't integrate all the way out to 6A or 3B or whatever it is, right, on the physical real charge. We don't want to tell Gauss's law that our charge is bigger than it actually is. Did I go too fast? Physicists, we like to solve a problem once. So we'll do it sort of generically like I've done up there, and then we'll start it and go and apply the special cases for the problem. But I don't have to like redo an integral or anything every single time on here. If I kind of solve the integral once and run with it. And by solving this integral once, of course, I mean knowing what my limits are. Our inner, our outer, for those different situations. I'm going fast because I want to make sure I get everybody's questions answered. Yeah.
11 on the homework?
Let's just do all the homework.
Yeah.
Yeah. Why not? This one was a little bit tricky, sort of. What's the trick? They're all point charges. As long as we're outside these shells, the electric field is going to be that of a point charge. As if all that charge were just right at its center, right? And because they gave us the center different distance, I can just treat this, which one's positive? This one's positive. So I can just say, oh, there's a positive charge at the origin. There's a negative charge right here. Tell me where the electric field is 0 other than infinity, right? Have you done this problem before? Think you did a force problem in chapter 21 where find the force is 0? And then in chapter 22 you did, I think, 2 different homework problems where we asked you to find like where the electric field is 0, some arrangement of charge, whatever. Where's the 0 going to be? Which of these is bigger? Shell 1 is 5, and shell 2, the blue one, is 1. So where is the 0 point going to be? Is it going to be in between? If I put an electric field somewhere right here in the middle, what direction will the electric field be pointing from this positive charge? That way. And where will the electric field from the blue one be pointing? Towards the negative one. So that's 2 vectors pointing in the same direction. Can you add that together and get 0? It's impossible. So there's no 0 point in between. Could there be 0 over here? There could be. Could there be 0 over here? Yes, same for the same reason. In other words, if we take a look at the directions, away and towards, they could cancel. And over here it'd be towards and away, they could cancel. But only one of those sides is going to work. Which side will it be? What do we have to be closer to? The smaller charge. Which one of these has the smaller charge? The bigger shell, right? So our position, we are kind of pretty sure it's going to be at whatever that position is, X, right? And so now we just set up a condition, right, where there's lots of, same way to write all of this, right? E1 plus E2 equals 0. The directions we've kind of already figured out. We know that one of them is going to be opposite the other. So when we solve that and we strip off the vector directions, we know we just got to set these things equal to. It's just a question of what it is. So what does the electric field do to shell 1? What's the distance to shell 1 to our point? It's just X, right? And then how far away are we from shell 2? Looks like it's X minus L, right? This distance in here is X minus L. Solve. Quadratic fun ensues.
So
Actually, you can kind of skip a quadratic a little bit.
I did all of this and I got stuck, or like I got the wrong answer. So then I went through the Go tutorial, and the Go tutorial says that the charge on shell 2 is, well, for mine it would be negative 5.6 times 10 to the negative 9. And then the one on the left is 5.6 positive times 10 to the negative 11. So I was confused as to why it,
So in my problem,
I thought it should be on the right.
I'm an idiot.
You gotta do that.
I did not read carefully enough, and I completely did not notice that that is a per area. That's not the charge on it, that's the charge density on it. So how do I find the amount of charge on shell number 1? By the surface area of shell 1. The charge on number 1 is 5 times 10 to the minus 6 coulombs per square meter times the area. And that area is going to be 4 pi r squared. And then the same thing for charge 2, which is negative 1 times 10 to the minus 6 times the area, 4 pi r2. Aha. Bigger surface area. I bet you it ends up that shell number 2 is the smaller charge. So shell number 2 is the smaller charge.
I confused you. It's the bigger one. Because the one on the left is...
Yeah, if shell number 2 is the bigger charge, then what region do we have to put our 0 point in? It's got to be over here somewhere.
I still got the wrong answer.
So that's X. So my distance, this is still X squared from charge number 1, right? But now what's the distance to shell 2? It's X plus L. So not X minus L, it's X plus L. Oh, that was tricky. Would I do that to you on the exam? No. Would I give you a problem that says find where 0 is for electric field? Sure, right? I've asked you like 3 times to do that, right? But I wouldn't try to trip you up. If I were to put this on an exam, I would either figure out what the charges are and just give that to you in the problem, or I would like bold the word density and surface and say, note, look at the units. But yeah. And math ensues. I could do the math if you want me to, but we could probably spend our time better. Anybody want to see it done? Yeah? Yeah? All right. Solve for x, right? All right, that's what I am working with. Let's solve that for x. I'm going to multiply both sides by this denominator and divide both sides by this other denominator. Where'd the k's go? They canceled out. And then I'm going to take the square root of both sides. This is an x plus L squared like that, because I forgot to write that down. So now this is going to be x plus L all over x, isn't it? Equals Q2 over Q1. That looks like x plus L equals x times Q2 over Q1. And if I move my L over to the other side and I move my x to the other side, something like that. And then I factor out an x and divide both sides. That means that I've got L all over Q2 over Q1 minus 1. I think I did my math right. Why did I reverse the order of the doodads in there? I had a negative sign over here, right? So I would have had a negative on top and then 1 minus that thing on the bottom. And if I factor a negative sign out of both of those things, this reverses, negative sign cancels. But I think I did that. Now, those of you that solved the quadratic for that, sorry, but you don't have to.
Where did the square root go?
Oh, darn it. Thank you. It was in my head. Because I square root that, so this is a square root, so that's a square root. It went along for the ride, and I ignored it. Thank you. Because it was, in my brain, Q, whatever that is, 2 over 1, was just a number. And it was a number square rooted, which is still a number, right? It's just along for the ride. It doesn't look like anything separate to me. So I tend to forget. And I probably would have plugged it in, got a red number, gone, what? No, I did it right. And then looked at it and went, oh, duh, square root. There is always a factor of 2 or a square root or a minus sign somewhere to haunt you. As an insight into my grading practices, what if you had done the same thing? What if you'd forgotten, you did everything and you set the problem up right and you were going in here solving and you forgot your square root? Would I mark it right or wrong? I'd probably mark it wrong, and then as I go back through and look and see why it's wrong, I might realize, oh, they just dropped a square root, and I would say -0 on your problem. Like you've set it up correctly, you've shown me you know the physics, and you made a math mistake. I'm not a math teacher, this isn't a math class. Should I demand perfection? Your engineering professors will do that. You'll learn that, okay? I want to know if you know physics. And knowing physics and knowing math are two separate things. So I tend to, because I'm also prone to dumb math mistakes, especially when you have all that anxiety surrounding an exam, especially when we have turned on the amnesia generators to full blast. You guys know we have amnesia generators in the walls, right? The new science buildings got super powered nuclear ones now, right? Okay, because you've all experienced that, right? You walk into a room, you start taking the exam, and what happens to your brain? It just goes blank, right? It's because the amnesia generators are on high. So you need to come up and ask us to turn them off. What do I mean by that? You need to come up and ask me questions, right? Because we got to get your brain into the right groove, right? For what's going on. There is an amnesia field in front of a whiteboard. I don't know if you guys knew that either. Have you ever been working in front of a whiteboard and you're sitting there going, what am I doing? And then you step out of the amnesia field? Oh, that's so. If you ever forget what you're doing, step back. The amnesia field in front of your iPad. It's real. How many YouTube videos have you watched that you have no memory of? Yeah. It's real. Other questions? Yeah. 13. Again, on this theme of let's just do the homework, Mr. Balogh. This always happens. It's good. You guys remembering your electric field stuff? Integral stuff? And stuff? Sphere, non-uniform. I feel like I've done this. Because I have done this. I mean, and not a few days ago. Like today, I've done this problem. Because this problem is that problem. Because they're both spheres. What's the catch?
It's the units. They're different units. And I was getting the right answers. I just didn't know how to convert the units over. It wants like millinewtons per coulomb or something.
There's a picocoulomb per cubic meter. And one's in centimeters.
No, for the answers. They want your answers. Millinewtons.
Oh, do they?
Yeah.
So there's the newtons per meter, but that one's going to be 0, right? Oh, total charge. That's just going to be coulombs.
It's -15.
Thank you.
Femtocoulombs?
Yeah, that's exactly, yeah.
Oh, yes.
Mr. Ragsdale, what's a femtocoulomb? Is that 10 to the minus 15?
Yes.
Femto. Is that 10 to the minus 15?
Yes.
Yeah, femtocoulomb, 10 to the minus 15. Right? Thank you. So if you've got, if your answer is 6.8 times 10 to the minus 15 coulombs, how do you write that in femtocoulombs? 6.8 femtocoulombs, right? If it was 6.8 times 10 to the minus 16, how would you write that in femtocoulombs? That would be 68 femtocoulombs, right? Because I got to write this as 10 to the minus 15. And how do I write it as 10 to the minus 15? Did I move it the right way?
Yeah.
Yeah. This would be 68 times 10 to the minus 15, wouldn't it? No. No. Not even I can do it. 10 to... Making negatives bigger moves it this way, doesn't it? No? It goes the other way? Sure.
Your students
Contagious, yeah.
It transferred over.
Yeah.
Maybe some of the feet, like,
So you would write it like that.
I'm cured.
Again, would I do this to you on an exam?
I'm so sorry. It's fine.
No. I mean, it's kind of... They should have... Wiley Plus should always just be asking for coulombs or newtons per meter or something, the standard unit for the thing. Millinewtons per coulomb? Sorry. Didn't mean to do that. So B is the electric field. That's going to be 0 because we're at the center, right? Yeah. And then, what is the magnitude of the electric? Oh, no, newtons per meter. No? Yeah, well, it'll okay. All right. Yeah. It's going to want it in, because newtons per coulomb would be the answer, but there wasn't a newtons per coulomb choice. Yeah. Yeah. Like we set up in that other problem, charge enclosed. Because it was uniform. Well, technically, we could integrate it, but we didn't because we just knew it was the total volume multiplied by that density. Yeah, and that's just because it was uniform. It was the same throughout. It's because this one is changing as R over big R that we have to integrate to be able to handle all the changes. Boom. Boom.
Oh, on the exam, do you want to have all the units in all of our work? Or is
Yeah, you have to have a unit on your answer.
Well, on our answer, but in our work.
In our work, no.
Okay.
Yeah. Yeah.
For C and D, for
confusing.
would be -3.
C and D.
Because it's still
So your picocoulombs, I would put that in as 17.2 times 10 to the minus 12 coulombs per meter.
Right.
When I did my calculation. The centimeters needs to be 5.2 times 10 to the minus 2. Right? So when you get your answer and it's somewhere in the neighborhood of -3, that's a milli. Yeah. Yeah.
I was doing that and was getting the wrong answer, so it might be my answer.
Yeah. You know, milli always means 10 to the minus 3. Micro needs 10 to the minus 6. If you forget that on the exam, what do? Come up and ask me. To me, that's a conversion factor. Now, is it better for you to just kind of know those prefixes? Yeah, you can just do things a lot faster, right? But during an exam, when you're stressed and things are flying out of your head and you just need somebody to tell you what it is, come up and ask me, right? You come up and ask me, Mr. Bale, how do I do the problem? Or some variation of that question, right? Okay. I'll say I won't help you, right? I try not to say I can't help you because I can, but I won't do it. So, yeah. Pico's 10 to the minus 12, nano 10 to the minus 9, femto 10 to the minus 15, atto for 10 to the minus 18.
You're not going to ask us that.
Atto?
Yeah.
No.
Okay.
That's a quantum. That's beyond quantum. That's like nuclear.
On 13C, I was struggling. I'm wondering, you're integrating from 0 to R over 2, right?
Yes.
And then the electric field would be divided by the big R. Well, no, you still. That's why it's not trouble.
So we have our sphere. There's our physical sphere. And in part C, you said C, right?
Yes.
We are at R over 2. So we're halfway through the sphere. So our Gaussian surface is somewhere in here. This is R over 2. So when we go in and do our Gauss's law thing, this is going to be E times 4 pi R over 2 squared, because we do the Gaussian surface. And then charge enclosed. Rho times 4 pi R squared dr. And then this was a function of a number times little r over big R. Number times little r over big R, 4 pi R squared dr. Integral. Integral's in the wrong spot. Integral. So constants come out. My A there is the number that they gave me. It's just a number. I don't care about it. Is big R a constant? Yeah. And then I got 4 pi A. So that leaves me with the integral of R cubed dr. And for part B, C, I need to get my physical dimensions right. We're going from 0 to R over 2. So it just so happens in part C that my Gaussian surface and my physical integral have the same radius. makes sense because we're inside the doodad. So now I should be good to go here. So this is going to be E4 pi big R squared over 4. And this is R to the 4th. Pi big R. R to the 4th over 2 to the 4th is 16. And then 0 goes in. I did that really fast, so I hope I did that integral right. There's another factor of 4, I forgot. Yep, there we go, got it. That cancels, this cancels with one of those, the 4 pi's cancels, that cancels and wipes out all but one of those. So my answer should be the number they gave me times R over 16. So this one right here, this integral is R, not that R, is R to the 4th over 4, isn't it?
Oh, yeah.
This is what happens when I start skipping steps. I make mistakes. But I think I got it. So this is going to be the number they gave me, 17.2 times 10 to the minus 12 picocoulombs, blah, 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 blah. My R is 5.2 centimeters, 5.2 times 10 to the minus 2, all over 16. I don't know why I'm infatuated with getting this number, but I am. Is it 12? -2 and 16. I got 5.59 times 10 to the minus 14. Oh, epsilon naught. All over epsilon, thank you. All over epsilon naught. 8.8, no, 8.85. 5 times 10 to the minus 12, right? So this number is 0.006316, blah, 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 which is going to be 6.32 times 10 to the minus 3 in whatever units I happen to be in. Because they want me to answer in millinewtons per coulomb. 6.3. Is that close enough? Yes. So then for part D on that one, and R equals R, how does my integral change here? For part D, I'm basically just going to lose a lot of factors of 4 somewhere. This will be R squared with no over 1, because it's not R squared over 2, because I would just put R in right there. And then over here, I shouldn't have used black, but over here on this side, this is just R, so there won't be any 16. This will just be R to the 4th over 1. So yeah, that's the only thing that changes. I want to teach you something that's going to help you on your exam tomorrow, and it's not physics. So I just need about 5 minutes of your time to explain something about how your brain works. What I'm about to teach you has been shown in numerous studies, particularly in physics, to improve student performance on exams. And it has to do with a psychological condition that we call stereotype threat. Stereotypes, we don't have time to really get into this, but stereotypes are ways that the human brain tries to make shortcuts when it comes to thinking about and categorizing people or groups of people. Nearly every single one of them is an oversimplification at best and downright mean at worst, and completely false. There's lots of different stereotypes that you come into contact with every day. And these stereotypes can be about your race, the color of your skin, your orientation preferences in a lot of different areas of your life, your religious practices, whatever. Okay? And when you are the target of a stereotype, when you're the victim of a stereotype, when you've been stereotyped for any reason, what feelings are you feeling when that stereotype is like just there? Feels what? Well, okay, so here's a stereotype that you've probably run into, okay? Those of you of the female persuasion. Women can't do math, or women aren't as good at math as men. True or false? Totally false. Totally false. And yet, when you hear that stereotype, how do you feel? Devalued? Bad? Depressed? Right? Okay? Men? Well, dads can't do anything. Dads are stupid. On behalf of dads, we are. But there are a lot of us who try. Right? And it just ranges all over the place. Okay? But in general, when a stereotype is evident, negative feelings are associated with it. Stereotype threat is a psychological condition where you may not be aware of the stereotype being present, but your subconscious is. And you're reacting subconsciously to the stereotype. And there is a stereotype everybody has about physics. What's the stereotype about physics? That it's hard, which is true. That is not a stereotype. It's so there, and I know you're already feeling it. Your brain's already locked onto it because I can see it in your faces. It's what you're feeling about tomorrow's exam. That I can't do it. The stereotype is physics is only for geniuses or smart people, and I'm not smart enough to do this. And it gets reinforced every time you sit down and fail at a problem, doesn't it? I'm not smart enough for this. I can't do this. You may not be sitting there like saying that to yourself. Some of you are like, yeah, I'm saying that to myself, Mr. Balogh, right? But it's still there, and it's still present, and it's still wrong. But what kind of mindset are you fighting against just simply sitting down in front of a physics problem? I'm asking you to try anyway when your brain is worried about this stereotype that only smart people can do physics. Stereotype threat leads to anxiety, stress, higher blood pressure, and if you're stressed going into exam, what is your performance going to be like? It's going to tank, right? So the question becomes, how do you alleviate stereotype threat? You have to recognize it first. Now, I know a lot of you are feeling what we call the, what's that called in psychology? Oh, imposter syndrome. You feel like an imposter. You feel because nobody knows how bad I am at this. And I look like I know what I'm doing, but secretly inside I am just a mess. And I can't do physics. I just can't do it. I'm an imposter. I don't deserve to be here. I'm an imposter. None of that is true. And why isn't it true? What piece of evidence do I have, actual factual data, that says you deserve to be here? What?
Because we're sitting in here right now?
Yeah, but not because you just walked in off the street and decided to take Physics 4B. What did you do? You passed Physics 4A. Now, if you completely lied and cheated your way through it, you are an imposter. But I don't think that's you. You passed. How did you get into Physics 4A? You passed calculus. Part 1. You deserve to be here. And you don't deserve to be here just because you passed some classes. There's a lifetime of experience, good and bad, that has shaped you and gotten your rear end into the seat in this classroom right now. Whatever those things are, whatever those hard things that you've been through, whatever good things you've been through, whatever clubs you did or didn't, whatever, right? You worked to be here, and you deserve to be here. What you need to do tonight is sit down and write down the reasons that you deserve to be here. They're going to be unique to you. The first 2 are freebies. You pass Physics 4A, you pass Calc 1. You deserve to be here. But think about other things that you have achieved, done, worked at, sweated at, bled at, in order to be sitting in this room right now. Write them down. Could be a bulleted list, could be a one-page essay. I don't care. I'm not going to collect that. I'm not going to grade it. Tomorrow when you walk into the room, I'm going to ask you to remember. I'm going to ask you to remember the reasons that you deserve to be here. And that's going to take your brain from being in a state of stereotype threat, where the stereotype of I don't deserve to be here because I'm not smart will be diminished because you're saying, no, I do deserve to be here. I feel like I'm not 100% at this. Yes, congratulations, you're beginners. But you deserve to be here. And you can do this. The only question that remains is at what level, right? And that's where I have to come in and judge. But don't forget that you deserve to be here. See you tomorrow. That was your coachy pep talk, by the way. Let me stop recording here.